Also, sure, stop spamming pings. Yeah, okay. Hi, I'm Rohan. I'll be talking a bit about Combigeo today. So, right, there are, it's hard to describe, honestly. Okay, mostly it's just combinatorics happening on a plane, mostly. Uh, so that's all there is to it usually. Like, okay, of course, that's not a good definition, but I think like that's what most of the problems you'll end up seeing in Olympiads will be. So you'll not usually need much more about the plane other than just like say triangle inequality or some basic results. Like you'll end up using some things like, of course, something very important which is always is the convex hull. Whenever talking about this kind of thing, the convex hull always comes up. Do any of you know what a convex hull of a few of some points on the plane is? These are the points on the plane. What is the convex hull?
Is this concerned about some convex set?
No, just some points on the plane. What is a convex hull? Okay, good to know. Convex
Are
hull,
points finite in number?
yes, yes. I should mention that for a finite number of points on the plane, what is a convex hull? Too many mosquitoes. Anyway, right. So it's just a set of subset of these points, which basically form a convex polygon, and all of the other points are either within inside the set or like or on the boundary. That's the convex hull.
Please repeat once again.
Uh, all points are either inside or on the boundary of this polygon, and this polygon is
Oh, so, okay. So there must exist a polygon such that all the points are either inside or outside. I mean,
no, no, all points are either inside or on the polygon,
yeah, okay.
and this polygon is convex. This is called the convex hull. Okay,
Okay.
So there exist infinite convex hulls for some set of points, right?
unique. It's unique.
But like just take it somewhat bigger, like
I
increase
mean,
each side by 1 centimeter.
these points are like parts of the uh, are also in the
Oh,
set.
okay, fine. Yeah.
Like the vertices of the polygon are a vertex like points in the set I was talking about. This is the definition I'm working with. There are other things as well. I'm not bothered with them right now. Sometimes it's defined with the whole thing inside also included. Sometimes it's just defined as the vertex. I'm not bothered. I'm just looking at this definition. Right?
Yeah.
Okay, nice. So this is what we'll be working with. This is very important, knowing your convex or how it, and it comes up a lot. Then you have the other standard idea, which is just ordering points by x coordinate, y coordinate, x plus y, like artificially imposing a coordinate system and x, y, or x plus y or something. Just artificially doing this, and that's okay. That's one other technique. Okay. Then you need to be comfortable with your. There are not many theorems that you usually use. Of course, there's like triangle inequality and all, but there's not many theorems. Okay, one theorem that is nice is Fick's theorem. Does anyone know what that is? Yes, perfect. So let's say you have this coordinate system and you have your lattice points. This is your xy thing. And these are your lattice points. And now you have some simple polygons here. These are all lattice points. Lattice points are like where the coordinates are both integral. So now the area is given by I, which is the number of points inside this polygon, plus b by 2, which is the number of points on this or on the edge, minus 1. This you can verify. Okay?
What is B?
The number of points on this polygon or inside.
So both including.
Uh, yes, like both are there. So b by 2 minus 1.
Okay, okay.
And
Wait, B
yeah.
is everything on the boundary and inside, right?
No, B is everything on the boundary or like a vertex.
Okay, so everything on the boundary or on a vertex.
Yeah,
Also, the polygon which you draw, should the vertices be only lattice points or it can be any random polygon also?
lattice points.
Okay.
I mean, okay, look at it this way. A random polygon can have a real area. This is like always x by 2 type area. So it couldn't have been random.
Yeah, fine.
Yeah. Okay, so this is Pick's theorem. Very simple, very nice. And then, okay, there's one last theorem. I don't know if you'll need it, but sure. Like, this is like as far as you might need with theorems. Oh, okay, I should mention this before saying any theorems. Okay, why I'm not 5. If you have k points in R to the k, you can, this is like a structure of R to the k minus 1 size. Like there's a unique R to the k minus 1 thing. Hyperplane, call it whatever. Okay.
Can you repeat?
There's a hyperplane. Okay, how do I say this? Fine. So let me say this. Any 2 points form a line. Any 3 points form a plane. Right? Any 4 points will form a 3D structure, and so on.
Yeah, fine.
Wait, so you can say there will be like k minus 1 independent vectors. Like,
Sure. Yeah, I don't want to use those words, but yeah. Like, not k minus 1 independent, then need not be k minus 1 independent, but like there will be k minus 1 vectors is all I'm saying. They just form a structure of, okay, this could have been on this line, right? So then it would have just formed a line. That's fine. I'm saying like the worst structure it could be if they're not collinear is a plane.
so maximum k minus 1.
Yeah. Like it's just not a big, not even a result, but it's just something to keep in mind because you might want to. So, for example, a plane intersecting a plane is a line. That also you want to keep in mind. Such things you want to keep in mind is all I'm saying. Yeah. So what are you saying? Somebody is saying something.
Can you explain Fick's theorem once again?
You have a polygon with its vertices at lattice points. Okay. Now, I is the number of points inside B is the number of points on the sides or as vertices. Then the area of this polygon is I plus B by 2 minus 1. Okay, good. Yeah, this is also is like a decent result and it generalizes well a bit. That is something if you are interested you can look at. And then there's Euler's theorem about planar graphs. What is this?
Yeah, E plus V minus. Oh, okay. Let me see.
Okay,
F plus V minus E equal to 2.
Yeah.
good. F plus V minus E equal to 2. What does this mean?
They are the
Face.
faces, vertices, and
Faces plus
edges.
vertices minus edges is equal to 2.
Yeah, but what is a face? Like, I'm what? Okay, like this is not on 3D structures. I'm talking about a plane.
A side you take as a, okay, that's edge then.
F is the number of 4 cycles, I think.
No,
Okay.
this is say a sexagon. What is like this is a hexagon. What is
Okay,
like,
sorry,
what
number
is-
of cycles, I think. Just number of cycles?
Sure. Yeah. No. Again, no.
There has to be like no point inside the cycle.
Yeah.
Yeah. Something like that.
I mean, okay. How many faces does this have?
2, obviously.
3 faces. Now 4
Yeah,
faces. Like the outside
I
thing
was
is also
lagging.
considered a face.
Oh yeah.
That is 1 face, 2, 3, 4. Okay. So face is like what you would expect. Just a cycle inside which there's no point.
Like in this fashion, can this, let's say the lower one and the top one, not form a face?
What do you mean?
Like there are three, three polygons. So the lower left one and the top right one, won't they also form a face? Like if you're taking a face as all the three.
What will I don't get.
I think Pranav is saying that if you take the top right one and the bottom one, and you took the union of those 2 cycles, then that should technically also be a cycle under this definition because there's no points on the interior.
Oh, the edges are all
Yeah,
okay.
so the edge
Like
is.
the edges also can't be inside
Yeah.
of the graph. My bad, I should have said that. Nope. Yeah. Sure, said something, right?
So like when you took all the union of all the three as one face, in that case also like you have edges inside, no?
What?
He's talking about the outside, not like the union of all 3.
Can you repeat, Pranav?
Like you took the outside, you said outside is also a face.
Yes.
So do you mean that the space outside these three these three polygons?
Yes.
Ah, okay, fine. Now got it.
Yeah. So yeah, okay. What Shaur is saying is basically it, but again, okay. Anyway, okay. Last theorem. 7, Helly's theorem. Anyone knows what this is? After this, we jump into problems.
I joined a little late. Just asking, will these be taken for granted? Like, are we just using them as results, or will we actually
Yes.
prove them as?
I'm just taking them as results. They're very common things. I'm not
Okay.
going to prove them.
Got it.
Like, okay, if you want to look at the proof of any of these, like, I wouldn't add much instructive value. You can just look at them.
Sure.
Like, instructive value relevant to the lecture. Let me put it that. So, does anyone know Helly's theorem? I'll pretend you know what convex is. So uh, for this, I'm going to talk about general k in R to the k, but what k you'll care is at most 3 usually. But in R to the k, you have some convex sets, okay? x1, x2, xn. Now, if you take any k plus one of these, and they have a non-trivial intersection, like a non-empty intersection, then the intersection of all of these k plus one intersection non-empty. Then x1 equal to 1 to n not equal to, okay. So if these are convex sets and the intersection of any k plus one of them is non-empty, then the intersection of all of them is not empty.
Oh, what is a convex set?
What do you know what it is for k equal to?
Not by, I guess, terminology, at least.
You don't, okay, what you know, okay. Like torus, right? What's it? Yeah, okay, figure it out what convex is then.
Sure. Oh, also here n should be greater than equal to k plus 1, right?
F symmetry. Sorry, what?
N should be greater than equal to k plus 1 here, right?
Naturally. I mean,
Yeah.
otherwise the theorem does not mean anything. You do not have a k plus one size set. Yeah, okay. So is this much clear? Now we'll try problems.
Wait, but like, what is like a convex set? Like, in general, like, what properties does it have?
I'm not defining it right now. Okay, just go with the k equal to definition. That your all diagonals are inside. That's all we'll work with for now. Like in general, if you want to look, Google. Sure. Okay. So till now, is there any problem other than? Okay, worst case you'll be work. Okay, you can look at it, I guess.
Could you just explain the Helly's theorem once again?
Okay, just ignore it. Okay, unnecessary. I was not sure whether I wanted to keep it. Let's just work without it for now.
Okay.
It's not. It won't be used. We won't use it today.
Okay.
Right. So let's start with this problem. By the way, I'm using Alex Remarov's handout as a reference for now. Okay. Like I'm
Okay.
using like some of the problems I'll be putting from my own handouts and all, but a few will be from Alex Remarov's handout. So he has a nice problem set, about 12, 13 problems on this. He has very nice handouts in general. You can check them out. Yeah, this problem. What? Yeah, okay. So any ideas on this? Okay, how? Thanks, Abhay.
Wait, so being able to pin two squares with the same pin just means they're like overlapping a bit.
Yes, yes. That's all. What does that mean? How do you start with a small number? How do you proceed? That's very vague.
Maybe like we find if suppose the color is green, we are talking about green color. So we first assume that none of the green squares overlap, and then we can find the minimum number of pins needed, and then we can somehow work with the structure and prove
What?
that.
Sorry, what? Can you repeat?
We like first assume that we are working with the green squares. So we
Okay,
first assume none of the green square overlap,
sure.
and we can find the minimum number of pins for that case needed.
Sure, why can you assume this, by the way?
I mean, like just for starting as of now, not like not the complete solution.
Okay, let me pretend that's fine.
Yeah, then we assume that let's say two of them overlap, and then find minimum number of pins, and then like
Oh, come on. How do you find the minimum number of pins? Like, that's the entire problem.
I tried for n equal to 3 case. It seemed a bit easy to do so. Okay, fine. For begin, it's hard.
Yes, please try.
I I'm not sure, but I think one case doesn't seem to work. Can you just check it once?
Sorry, what?
Like n equal to 3 case fully doesn't work. Like for one case you need 5 pins. Can you just check it once?
Can you actually just send me a picture of the diagram
Yeah,
that
yeah,
you have? Like
yeah, yeah,
just
sure.
send it to me on WhatsApp.
Yeah, sure. One sec. Yeah, I sent you.
Okay, I'll check. Yeah, I'll check.
Uh, I have a weirdly vague solution that is still giving me some amount of confidence. Um,
Sorry, just a second. I use one pin to pin O. I'm done.
Oh, I thought you have to do for all colors. Sorry.
Yeah, okay. Go on. That's it.
right. So I was saying that this is a very vague, but I still kind of want to throw it. So I was considering like a phase space where the x-axis has, so if say the colors are 1 to up to n, and
Okay,
I'll name the squares a1 a2 up to a capital N, where capital N is the number of squares.
fine.
Okay, so and so the x-axis has 1 to up to n, and the y-axis is a1 a2 up to a. And then I plot. So if a1 has color 1, then I'll plot it as a1, like I'll plot that as a point. If a1 has
Okay.
color 2, and so on. So then I have a total of capital N points, and so I have a total of capital N points in my phase space. I'll join 2 points if they overlap
Okay.
by an edge. So what the problem statement tells me is that if I take any n collections of different colors, then I can then I necessarily have an edge in that subset of the full set.
Sure, but there's one main information lost. This is on a plane.
Ah, okay. So maybe the resulting graph doesn't have to be planar. Is that what you're saying?
Not planar, but like, I mean, like you're just losing the fact that this is on a plane.
Oh,
Uh,
right. I forgot the
like
thing.
this is not graph
Right,
readily.
right. Got it. Okay.
You're saying that we can induct. How? That's good. Induction is a good idea, and people have raised it before. But how do we induct? Also, okay, someone tell me k equal to, sorry, n equal to some, yeah. Okay, tell me what happens when you try to induct. So how do you try to induct? You start naturally. The thing you try to do is you start with a square and pick it among the collection of n things that you have, and you can now say that. Now you can say what actually? Yeah. Some squares would be intersecting it here. 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 Now you would try to delete this, and all squares adjacent to it, and say, okay, now I'll pick my rest of my things in the remaining set. Yes, like that is the natural method of doing things, right? So now you try to pick a remaining set, and now you can argue. What can you argue? You needed 4 pins here. What more pins do you need?
I'm sorry, I kind of missed it. Could you repeat? Like, are you telling your solution or?
I'm not telling a solution. I'm saying like, what can you try? You'll try to induct. You'll start by picking a random square and seeing what intersects it, right?
Yeah.
And now you would like this square would be in your choice of n squares that you're picking that intersect at some points, right? Usually.
Yeah.
So now that you remove all of these, which are adjacent to it, and now you try to pick n minus 1 of the rest.
Okay.
That's what you ideally try to do, right? Now in any choice of n minus 1 of the rest, there should be an intersection. Yeah. Like there must be two that are intersecting. So you have basically set the same problem for n minus 1 colors. But the bound you know for n minus 1 colors is 2n minus 4. If you somehow have inducted. But now you have 4 more pins. So this is 2n, which is not the bound you wanted. How can I fix this?
Is this going on for 2 colors, right?
Okay, what I did was I'm trying to induct, right? So what I do is I pick a random square, I consider all that is intersecting it, and I remove all of that. In the sense, I ignore all of that. And now in the remaining problem, I try to work.
Oh, okay. So how does it reduce to n minus 1 colors?
In the remaining problem, because I've already picked this of whatever color I had, right? I'm trying to pick n minus 1 of the rest, right? And 1 square of each of the other n minus 1 colors.
But now, how can we ensure the condition that any n squares of pairwise different colors?
We know that n squares of pairwise different colors in among the n minus 1 and this, none of them are intersecting this. So there must be two among those which are intersecting each other.
Wait, what squares are at the corners again? Yeah, like the stuff at the corner.
Just some squares which are intersecting this. I don't know. I just picked the like. How do you induct? Okay. How do you try to induct? You just try to pick a random square and see what's happening around it, right? And see what happens if like you pick this square among your n selection. Now, if you're trying to pick n squares, you don't want to pick anything that is already intersecting that, because that is not giving you new information. Yeah. So now you're just trying to pick from the remaining n minus 1 colors which are not intersecting this thing, this square. But when you pick from the n minus 1 which are not intersecting this, with the condition that you already have, 2 of those must be sharing some area.
Yeah.
So when you remove all of the neighbors of this, you have the same problem on n minus 1 colors, is what I'm saying.
Oh, but the thing is, you have not. But okay, you pick among any n minus 1 squares of pairwise distinct colors, but on the board there are squares of n colors. No.
Yes, but among those n minus 1, with 2 n minus 4 pins, I'm able to color, like completely use all of, like pin down all of a certain color, right?
Oh, we just ignore one color, you mean, in that scenario?
Sure. I mean, I want to just do it for a certain color. So for a certain color, I'm able to do it in the rest of the grid with 2 and minus 4. And the ones which were intersecting this square, I can do it with 4 more pins.
Yeah, but the thing I was saying is, the problem states the squares are of n minus 1 different colors, and you choose n minus 1 squares, right? But after you remove,
No, like you choose n minus 1 squares of pairwise distinct colors.
yeah, that's what I'm saying.
Okay.
N different colors of squares, and you choose n squares of pairwise different colors.
Yes.
But after you remove one square, there can
I
be,
didn't remove one square. I removed the neighbors of the square.
yeah, okay, yeah. I mean one square and the neighbors. It's still possible that the squares lying on the board are of n different colors.
I'm not removing this square. I'm picking this square. Like that's what you're trying to do, right? You're trying to pick one random square among your selection of n squares.
Oh, okay, now got it.
This has been picked. This is of color 1. Now you can't pick any more color 1 squares.
Yeah, fine.
And I don't want to pick anything neighboring this because that is not adding information. Then I just know that they're already intersecting. But the thing is, now when I can find a color in the rest, which can be done with 2 and minus 4 pins. But some of its squares might have been intersecting this original square, which is causing 4 extra pins. But the intended thing is 2 and minus 2. So this should have
I
been,
think I've got the fix.
yeah, go on.
Just pick the rightmost square.
Yep, just pick the rightmost square. Now
Yeah,
every square
nice.
must be intersecting either of these ends. So done.
What do you mean by rightmost square?
Highest x coordinate
Oh, okay.
of the center, let's say. They're all identical paper squares, so the remaining must be intersecting this vertex or this vertex, and I'm just adding 2 then.
Wait, could you explain the solution again?
Yeah. So what I do is I start by picking the rightmost square. I'll tell you in solution form now. I start by picking the rightmost square without loss of generalities of color n. Okay. Because colors have not been distributed or named. This is of color n. Now the remaining squares are either intersecting this in some place, either of these. Like, because this is the rightmost, they can't be intersecting further back. They can be like this, but nothing other than that. So now I try to, whatever squares are here, I ignore these squares. Now in my remaining plane, there are, in the other n minus 1 colors, if I pick n minus 1 squares there and this square, I know that 2 must be sharing a point. Yes? Two must be sharing some area, right? So if among the arrays, 2 are sharing an area, I can basically, but none of them are intersecting this square. So I can pin them down using 2 and minus 4 colors. Like, sorry, 2 and minus 4 pins, I can pin down a certain color. But what are the things I ignored? I ignored the ones intersecting at this vertex and intersecting at this vertex. So I can add one pin here and a pin here. So I added 2 pins and I covered everything of that color. Make sense?
Wait, how are you accounting for the color of the rightmost square?
I
Isn't this-
I don't care. I just need to prove that all squares of a certain color, of some color, all squares are covered. I
Oh,
covered
okay.
all squares of some color here, and I just used 2 pins to cover all the remaining squares of that color itself.
Okay.
Does that make sense? Okay, this problem 1, this is Russia 2000, I think. Yeah. Okay, nice. So let's look at something else. Okay, was this clear for everyone firstly, before I move on to another problem?
Yes, sir.
Okay, also please don't say sir.
Just a question, and this is just like a pedantic question. In the last problem, when we say pin down, we meant like there is at least one pin that is pinning down the square, right? Like you don't need to pin
Yes.
it down at all 4 vertices or anything.
Yeah, you just have a pin going through it. That's
Right.
all.
Then it makes perfect sense.
Okay, the second is, I don't know the source of this. I've shared this with quite a few people, so some of you might have seen this before. Yeah, Pranjal posted it on EOPS, yes, but he had given it to me way before that, so that is not the source. And it's not his own problem. It's like not standard Combigeo, but okay, there is something to be said about it.
Wait, aren't all of the sides of like each parallelogram parallel to like the other parallelograms as well? Pretty much.
What?
So like if you have like two parallelograms, they have like two sets of parallel sides. So then between those two parallelograms, the sets will be parallel to like each other. Sort of.
Sure. Okay. I'll give you an example of what the problem is saying, if that helps. And you can tell me what the confusion is. Then 74. Okay. How do I make this? Sorry. Yeah. Sure.
Okay. Okay, never mind. I was wrong then.
This is just one construction.
Also, is 2021 unique here?
What do you mean?
Like, is it true for n comma n minus 1 parallelograms also?
Let's say it's true for n comma n minus 1. That means you can do for n, then means you can do for n minus 1. That means you can do for n minus 2. That means you can do for n minus c. That means you can do for 1. Can you do this one? 1.
No.
There's your answer. Good question, but ask yourself the question as well.
Like the size of the parallelograms need not be same, right?
Sides of the parallelogram might not be same. What do you mean? Like,
Like of the first 2021,
yeah,
they need not be of the same size, all right?
yeah, they don't need to be of the same size. Like I could have done this with, uh, I did this right now. Like this, I did it. But I can just as well create another one here, and create another one here, and create another one here.
Yes.
Create another one. Okay, for those of you who have seen this before, I'll add a couple other problems.
I guess so. I have an idea.
Okay.
It's like if you consider the point, can the okay, like if you consider the vertices of the parallelograms,
Hmm.
look at the convex polygon, and we consider two uh, adjust I mean adjacent vertices.
Okay, like this.
Yeah. So it's like we consider the can you label them, like it might,
Yeah, sure. Maybe.
and also the ones which yeah, those ones, yeah, the okay. uh, yeah, so it's like in the segment BC there will be the a point which is like closest to BC, and also like a vertex of a parallelogram.
Like this, you mean? Or this?
I mean on BC. Oh yeah,
Obviously.
yeah. I guess yeah. Uh,
Okay.
uh, okay, yeah. I think there's some flaw in my solution, but I'll and we uh, also see. I mean, like for the point A, it's like we again like look at the points of parallelogram on BC and AF. Does it make sense or? Like if yeah, A is a point on a parallelogram,
Hmm.
then we consider the points of that parallelogram on AF and B, AB.
Okay.
I'm not sure. Okay, yeah, like I don't think that's always possible. So yeah.
No, no, it's okay. Take a moment and like try to formalize it.
Yes, yes.
I have got an idea, I think.
Haven't you done this before?
No, actually, I just asked you for that, but I didn't follow it up later.
Okay, okay.
Uh, I was motivated by him marking that side. So we take any side AB
Hmm.
and then take the opposite side in the parallelogram.
Okay.
And then there will be some side of another parallelogram which connects to it, and
Okay.
take the opposite side of that parallelogram.
Okay. For
Because
example,
all these lines are parallel,
just
we
a
are
second.
traversing.
Just a second. Just a second. If I start from AF, I go
Yes,
to this line. Now where do
yes.
I go?
And choose any of the parallelograms touching this. There are three. Choose any of them and pick their opposite side.
Okay, and just keep doing this.
Yes, and because all these lines are parallel and we are moving in one direction, we
Hmm.
are effectively uh, increasing the distance from AF,
Sure.
from segment AF. So, because this is a convex polygon, it must these set of lines must end, and when they end, it is the side of the polygon.
Good. Okay.
So,
I
all in
end
all,
up
we
with
have that every side in the convex polygon has a side has maps to another side which is parallel to it.
okay. Sure.
Yeah.
Very good. But what now?
In fact, I think these will be exactly opposite sides.
Very good. How?
Yeah, as I said, I think so. I'm not sure why. I'll should be something very obvious.
Yeah, yeah, it's pretty direct. You're right. You can say something stronger also, like not just parallel. There's something stronger to be said.
Even number of sides in the
Yeah, they are the same side lengths
Good. How?
because you just keep summing all of them. I mean, you project, you look at, you think this is a 3D structure by
Okay.
projecting it upwards on the paper and look at it from uh, uh, what above AF, if I can say, and you will see
Okay.
that
Yeah, I
all
kind
of
of
them.
understand, but yeah.
Yeah.
Yeah, okay. Sure. Makes sense. Good. So that is true. Now you have found that opposite side lengths are parallel and equal. Also, why are they opposite? How are they equal? Do you want to repeat, Vedant?
Okay. Let me try my best. So we consider the set of parallelograms which connect to segment AF. Suppose this is set S naught. Then we take all the opposite sides of parallelograms in S naught and consider all the parallelograms which connect to this S naught dash. That is opposite sides of parallelograms in S naught. We take the new set of parallelograms as S1 and take S1 dash and keep doing that until we reach the side which is parallel to AF. And because all this all the side lengths uh, in each set, all the segments in each set have this same sum, uh, the corresponding side in the polygon has the same length as the original section.
Yeah, that is good. Also, you can do this type of argument that you are just okay. Sorry. Yeah. So when I started from here, this carried over here and went on till here, right? So I can just mark this as corresponding to this part, and from every part I can just do it, and I'll eventually get something here. So you can basically say that this length is at most CD and reverse argument for AF, so AF equals CD.
Also, they're opposite because if they're not, then I think the polygon cannot be convex.
Yeah, that's it. So there, yeah, that's now what?
Yeah, after that, I think I have to.
After that,
After that, I think I understand. It's like, it's like for every quadruple of parallel pairs of parallel sides, we have a parallelogram formed by those. So then
yes,
like,
yes, yes, yes.
yeah, and then sort of
Yeah, perfect.
then I just the construction part, which I'm sure is easy.
Oh,
But
yeah,
I'm bad at construction.
leave the construction. Can you just say the rest for everyone?
Okay, so right now we have the fact that I mean the discussion is led to the fact that the polygon has even number of sides and opposite sides are parallel and equal in length. Now what I'm claiming is that so basically we have n different parallel pairs of lines, right? So for example, in this hexagon, we have three different pairs of parallel lines: AF and CD, AB and DE, and BC and FE. And observe that in the construction of three parallelograms that was made by Rohan at the beginning. So if we take the slope corresponding to AF and CD and take the slope corresponding to AB and DE, there's a parallelogram formed by these, which is ABXF. If you could just label that X.
Okay, there's an easier way to do this. I'll just say it.
Okay, yeah, sure.
So with this parallel line,
Can I say before that?
yeah, sure.
Like in this way, if the number of pairs of parallel lines is greater than 2020, won't that exceed the construction?
I mean, then it's just not tileable even with 2021 parallelograms.
Yes, fine.
Yeah, I think this 2021 implies that it's also reliable by 2016 because
Yes,
that's
exactly.
the next n choose to form number, and then
Yes.
you can always increase by one. Yeah.
Yes. Yeah, so the thing is, like, AF is, let's say, parallel here. So I just join this. Like, I'll create a parallel line here randomly. I'll create a parallel line here, 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 and I'll keep going. Okay, like, even if it was a weird shape, like if it was asking me to do this, do this, do this, do this, do this, I'll eventually reach CD. Yes, because I'm just going to the opposite ends. And similarly, I can start from AB. Do this, do this, do this, do this, do this, do this. From AB, I'm reaching DE again. So these two lines must be intersecting somewhere. Because of a line going from AF to CD, opposite, and AB to DE, these must be intersecting somewhere. So because this was a parallel side inside a parallelogram, and again, parallel to the side of a parallelogram, I must have had a parallelogram here with a side parallel to AB and a side parallel to EF. Side parallel to AF and AB. Yes? Like this point is on a line inside a parallelogram which has a side parallel to AF, right? And it's also inside a parallelogram which has a side parallel to AB. That's how these lines were made. So for every pair of parallel lines, like non-parallel lines, there is a parallelogram. So n choose two parallelograms are at least there. If it's a 2 and gone. Now for construction is actually pretty easy. let's say I have a 2. I'll just make it easier for myself. Like, let's say this was the thing, then I make this. This is parallel to this is parallel to this. Now I just go here, parallel here, complete parallelogram here, and I'm here. Like, I just keep taking the next side. I start with these two, I'll end up with something here, and I continue with these two, and I keep going. I basically used n minus 1 here with each pairing, minus 1. And now I'm reduced the problem with, I now have n minus 1 sides here and n minus 1 sides here. And I can repeat the construction. So this is basically the n choose 2 construction. Because obviously 1 plus 2 plus dot 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 till n minus 1 is equal to n choose 2.
Oh, I understood the construction. What's the use of n choose 2? I don't understand.
I mean, the bound we got was n choose 2, right? Like, there are n choose 2 like n pairs of parallel sides. So there are at least n choose 2 parallelograms, because for each pair of like each choice, like if this was AF and AB, there's a parallelogram with sides parallel to these. BC and AB, there's a parallelogram with sides parallel to these. So there are at least n choose 2 parallelograms. And I showed that you can always do with n choose 2 parallelograms. Since, like, now if I have any number higher than n choose 2, does not matter, I can do with n choose 2. As long as it's not at least n plus 1 choose 2. So I can do this with at least 2016 parallelograms. So now you can just split some parallelogram into 2 and increase till you reach 2020. Good. This was the problem. Make sense?
Rohan, I had an idea, but I'm not sure how to proceed. Can I share?
Yes, sure.
Like, if we can we somehow prove that two equiangular parallelograms have a side in common, so that later we can cancel out that side and prove it?
Sorry, can you repeat?
Two equiangular parallelograms means they have the angles same
Okay.
and are inclined in the same way, so we can cancel out the side that they have in common and then prove that there is one less. We can do with one less.
I am not even sure what that means. Ah, that way. Yeah, I don't, like, how will you combine them if they're far away or something?
Yes, that's what I'm asking. Can we proceed somehow? Do you have any idea?
I don't know.
Okay.
I mean, okay, like, you just have to reconstruct, I think. Like, you just have to start with a new construction. You showed that you can do it with the n choose 2. That is a new construction. Now you can reach 2020 again. You don't know how the 2021 construction is looking like. So it's not
Yes.
necessary. Yeah. It's quite a nice problem, like, yeah. Yeah, do you want to try 2.8?
Question: what does translates mean here?
Just you take it and drag it here and
Yeah. So,
you
so like by the translate we mean like a triangle, right? Not the actual translation.
I mean, I
But
have been given. See, the point is like the orientation is not known
no,
and the size.
I'm saying that I say that a triangle A is a translate of a triangle B if I can move B in the plane so that I can reach A. Right, okay, translates equals translate, copy, got it.
Sure.
But like they're like we can't rotate, so they have to be parallel after the translation.
How do you define parallel? What do you mean parallel?
The sides are corresponding side. Like for two translated copies, I can find like parallel sides.
Sure. And equal size as well. Like
Yeah,
not
yeah,
just.
that's yeah, yeah. So, okay, cool.
Also, what's this letter, by the way, if you know? A Greek letter, I mean.
I'm just going to call it G. Uh, Away like till what time do I have?
Yeah, they're usually 8:30.
Cool.
You can extend by 5-10 minutes if you want.
No, no, it's fine. Let me do some other problem then actually. Like
Okay.
you can try these on your own. I'll not say anything about difficulty actually. Then people just don't try. Uh, right. I just want to try this problem from Taiwan. This is from 2021, I think, itself. So, new problem, yay. Yeah. Quiz. I mean, I did not say what position it is on the paper. That is like the relevant part. Anyway, it's a quiz. Quiz don't have difficulty positions anyway.
Oh, this problem. I did it a few days ago. Yeah.
Yes, yes, I saw. These problems you can try if you want. These are nice.
I'll just take a screenshot quickly.
Yeah.
Okay, I can change it.
It's quite a nice problem, honestly. I like it.
So basically, we have one information that n of x is not equal to x, right?
I mean, yes, yes. Yeah, n of x is not x.
No, n of x, n square x, I mean.
It can be.
Oh, for n greater than 2. Like if it is, then
N
only,
greater than 2? Oh, small n. Yeah.
yeah.
It can be. It can be.
Like
Why
if
not?
it is, then won't that two cities will be isolated?
No, like some other city can have that as the n of
Okay.
x as well. I mean, n square x will have to be x if like you have the smallest side.
Yeah.
The roads are bidirectional, right?
What? Yes,
Like,
yes, yes, yes. You can use a graph theoretic interpretation and say these are undirected edges if you want.
yes.
So if we take the graph theoretic notations, then I think the shortest edge has to be bidirectional and the others can't be, because then it's just not connected.
Sure. I mean, all edges are bidirectional. Like, if you can go from A, you can go from A to B, then B, you can go from B to A. It's fine. It's a road connecting X and N of X, not a road just from X to N of X.
So if we consider the graph theoretic interpretation,
Hmm.
what we will get, I think, is a spanning tree and an extra edge, which means a cycle and branches coming out of each vertex of the
A
cycle.
spanning tree and an extra edge. Why is there an extra edge?
Because, oh, so two cities can have the same.
Each other as the neighbors. Yeah.
Yes, yes.
Ah, yes, and that will be for the shortest side. So we have a spanning tree.
Okay.
Okay. So every other side. Okay.
Oh, what's a spanning tree, by the way?
A spanning tree is just a tree that covers all vertices. Like, you don't need to have the full graph. Like, for a big graph, there's a spanning tree, which is a subgraph.
I was just thinking maybe we could do like a bounding, and like I came up with like a very stupid bound, which is that the number of suburban cities is at least greater than equal to the um. Okay, wait. No, no, just mind my whole issue is that like every edge should, in the most ideal case, every edge should correspond to a suburban city. But
Okay.
the thing is that edges can sort of end in the same vertex, so that could like reduce the number of suburban cities. So like I was thinking we could probably try like a bounding, and I don't know if that would work. Like, a bounding on the number of edges based on the number of edges.
No, that's decent. That's a good idea.
Okay.
Yeah, one thing more.
Hmm?
One edge. So we say A is near B if A has the shortest distance to B.
Uh, I mean, A is B of N of B. You mean?
Yeah, so that is defined. Okay. So suppose any vertex B can have at most six uh, AI such that
Is 6 possible?
six yeah, six is not possible. Okay, so at most five
Yes.
AIs such, I can't frame it, but you get the idea.
Yes, yes. Okay, so what he's saying is for any x, then the set n of y such that n of y is equal to x, the cardinality of this is less than equal to 5. Yes? That's what you're saying, right, Vedant?
Yes, yes.
Okay, go on. Proof.
Angles.
Good.
We consider x and at most 360.
Yeah, perfect. So he's saying that you have some things here, and let's assume there are 6. So these 6 you have. Now these angles sum to 360. So at least one of them is at most 60 degree. Let's pretend this is the one which is 60 degree. Now in this triangle, this is 60 degree. So now at least if neither of these angles are greater than 60 degree, then all of these must be 60. It must have been an equilateral triangle, but then this couldn't have been n of x because this is not strictly smaller than this. This is equal to this. But now, if this is the shortest, if this is smaller than some angle, if this angle is theta and this angle is smaller than theta, then observe that this length must be smaller than this length. So n of this must have been this, not this point, not x. N of y must have been y prime, not x. So we get that this is at most 5. Good. Frame 1, this size of the set y such that n of y is x less than equal to 5. Good. What now? Vedant, can there be a cycle?
No, because it is a spanning tree, right?
Why is it a tree?
Because if we considered that uh, every uh, that an edge from every vertex went to created a different edge each time, there would be n edges.
Okay, good.
But we know that for this shortest side,
Yeah,
there would be two edges overlapping.
good.
So there are at most n minus 1 edges, but we know that the graph is connected, so it is a spanning tree.
Good. Also, the word is just tree. You don't need spanning because it's just a
Yeah,
tree.
yeah. Okay, the graph is a tree.
Can you repeat the bound for n minus 1 edges?
He said there are total n edges. Yes. If you connect x and n of x. Yes. But in this counting, shortest edge counted twice.
Yeah.
So n minus 1 edges. Less than equal to n minus 1 edges, but since since it's connected, there must have been n minus 1 edges. And it must have been a tree. Does everyone know what a tree is? Okay, if you don't, you'll know tomorrow. So there are at most n minus 1 edges. Now, okay. What are the vertices which are not? Okay, go on, Vedant.
I think I think now we root the tree somewhere
Okay.
and uh yeah, and make its children nodes and so on. So we start from the leaf node and
What kind of a thing is a leaf here?
leaf which is the end of a chain. I mean,
Yeah, no, okay. So can n of the
and
vertices which are not n of
we
x but
take
anything.
the penultimate of the leaves, I think.
Okay, no, what I'm asking you is consider the things which are not n of x. Are they leaves or not?
And not n of x. Just a minute, let me think.
They are like it like go like
Good.
yeah, I mean it just you mean kind of binary tree structure, right? By a
What?
leaf.
What? No, no, I have nothing rooted. I just have a graph. A leaf is something which is degree one, with just one edge going through it. That's all I mean by leaf.
Oh, I misunderstood them.
Yes, so whatever is not and whatever is not suburban is a leaf. Yeah.
Yes, very good. So if I remove all the non-suburban things, the remaining graph should also be a tree.
Yes.
Good. So if I had, let's say, k non-suburban things, sorry, k suburban things, in this tree, how many edges are used? Just like when I remove all the non-suburban things, how many edges are used?
K.
K minus 1.
1.
K minus 1. Okay.
Yeah. Okay. How many edges are total there at most?
N minus 1.
Okay, like what is the total degree? Like what is the total number of edges? Like sum of degrees
N
is
minus 1.
5k
Total
minus
number.
k minus 1, right? The
Wait,
total number
isn't
of edges is this, right?
the total
Because
number of edges is n minus 1, right? Am I
I mean the total number of edges is less than equal to this as well.
Oh
Because
yeah.
Yes,
sum,
yeah.
sum of all degree minus The
Yes,
edges
yes,
which are
yes.
counted twice.
Yes.
This is what? So n minus 1 is less than equal to 4k minus 1. Sorry, 4k plus 2. Which means n is less than equal to 4k plus 2. Sorry, n minus 1 k is greater than.
N minus 2 by 4
Yeah.
is less than equal to k.
Which is the bound you wanted.
Yes.
Yeah.
Oh, how did you get n minus 1 less than equal to 4k plus 1?
This is the total number of edges.
Yeah.
This is an upper bound on the number of edges
Okay.
from here.
Oh, by the way, can you then repeat how it's not a leaf? Oh, how it's a leaf, the non-suburban cities?
If it is not a leaf, like, okay, how many edges does it have? Because like only the edge going from it, right? If I direct edges from x to n of x, then it has only one edge, the one going from it. There's no edge coming to it because it's not a suburban city by the definition of suburban city.
Oh, yeah, it's fine. Yes.
Yeah, that's it.
Oh, also there is a
What's the
question.
5k minus? What did we do there?
The total degree, like when I do the degree sum of the k vertices, if I just from the k vertices, I sum the degree, that is 5k. But when I sum the degree, I double count the edges which are between two of these. Yes,
Right. Got it.
which I remove.
Yeah.
Yeah. Is there any other doubt?
There is a question in the chat. What do you mean by rooted?
Yeah. Okay, that's not relevant here. We never use that. Again, if you want, you can look up a definition. Oh, cool. Oh, okay. Right. Any other doubts? I'll compile a small problem set. I'll actually keep it small for once and share it soon if you guys are so inclined. Oh, I have no idea. Not getting the time.
I'll stop recording, right?
Yeah.